Get started is, I have a very long connection to this school because I was a student in the very first ever National School on Neutron and X-ray Scattering. That's when it was still completely held up at Argonne because they still had a neutron source there. Now you get the opportunity to see two national labs, so enjoy it to the fullest because I still have fond memories and I still have connections to other students that attended that school with me. Some of them are now in Europe. You know, this is a place to network and to really start your own professional network because you'll be future colleagues in a few years, you know. So my topic today is an introduction to powder X-ray diffraction, and so no, I don't take offense in people wanting to grow whatever size crystals because I don't really work with big crystals. I work with powders. So if we look at that one, the first thing I want to put up here is a little bit of the history of powder diffraction. Because pretty much everybody tells you that X-rays were discovered in 1895, right? And the diffraction of X-rays was discovered in 1912 by von Laue. Then the Braggs came up with the diffraction laws in 1912 and 13. That's often considered the birth of crystallography. Turns out powder diffraction is really not that far behind. It was developed independently in two countries. Debye and Scherer in Germany came up with it in 1916, and Hull in the United States in 1917. Now, back then, when everything was still done by typewriter and publications were put together out of that, a year in between really means that people kind of discovered it independently. Okay, nowadays, if you discover something in 2016, nobody else will be able to publish it on another continent in 2017. But back then, communication just took a little bit longer. Now, the very original methods are actually film-based, and I'll have an example of that on the next slide. The first commercial powder diffractometer actually came out in 1947, and it was brought out by Philips. And this is a picture of this very original powder diffractometer. And if you have ever seen a powder diffractometer, it may look a little bit different, but the general setup really hasn't changed that much, has it? You still have a diffractometer circle. You have a tube somewhere, you have a detector mounted somewhere, and your sample in the middle there. Of course, the optics have changed a lot, the detectors have gotten a lot better, and so the experiments have gotten a lot better, but the basic design of the powder diffractometer is still very similar from what it used to be. So this is what the original setups look like, okay, the non-commercial diffractometers. This is a so-called Debye-Scherer camera. And so basically what you have is a metal cylinder, and you mount your sample in a capillary in the very center of it. And then you have a collimator, and you put your X-ray tube in front of that. And then you have a beam stop on the other side, and you have a piece of film on the outside of this cylinder. Now you can imagine that using something like that nowadays would be a complete nightmare because radiation safety would be all over you because there's no shutters on this thing, okay? You basically just have an X-ray tube sitting in front of a little collimator, okay? Here's what you get out of that. So your film has holes because you need to somehow get around these collimator and beam stop areas. And you get these lines on there, which can be curved depending on where on this film they are. And you have to basically measure the distance from your holes, and then you have to use the radius of your camera to figure out what angle that corresponds to. So a lot of manual work, okay? And of course, film isn't quite as good when it comes to detecting the intensities, okay? But this is the very original setup, very simple, very cheap, could be manufactured in most machine shops. Now, let's talk a little more about powder diffraction. And the first thing to point out is that the physical basis of powder diffraction is exactly the same as what you've heard so far in Christine's talk for single crystal diffraction and in all the lectures up to this point. We still work with Bragg's law. It gives us the location of the peaks, and our intensity of the diffraction peaks is still proportional to the square of the structure factor amplitude. Now, just a brief reminder, we are talking about both X-rays and neutrons in this school, which is something fairly unique because many times people only talk about one of those types of radiations to you. The structure factor equation on that last slide did contain a factor that describes the scattering power of the atoms, and that will be very different depending on whether you use X-rays or neutrons. For X-rays, we call it Fj, or form factor, and it depends on the number of the electrons in the atom, but also on your sine theta over lambda, or Q, okay, on your diffraction angle. It does undergo very large changes when you're close to an absorption edge, and especially in powder diffraction for certain types of experiments, we actually make use of that, okay? For neutrons, we call the scattering power the scattering length Bj, and it depends on the isotope and is pretty much independent of Q, okay? The interesting fact is, Bj could be negative for some isotopes, so that makes it very easy to spot certain atoms in your density maps as you transfer them. But the important thing to keep in mind is this, okay, that you have a drop-off in the scattering power for X-rays with angle, while you do not really have much of a drop-off when it comes to neutrons, okay? And that can often give you a lot of detailed structure when you go to the smaller d spacings in your resolution with your neutron data. And especially in powder experiments, you can really get a lot more data than what you could get, for example, with an X-ray experiment, especially in the lab. And this is just a slide that kind of shows you what is meant by how these scattering powers vary. So for X-rays, number one, you have to worry about the angle at which you are, and then it just strictly depends on the number of electrons. While for neutrons, a lot of things are a lot more comparable. So you don't have that one heavy atom outweighing everything else, and you can have these negative scattering powers, and sometimes you can distinguish isotopes of the same element. Now, I did say that Fj can undergo pretty dramatic changes close to an absorption edge. That is what we often call a resonant X-ray scattering experiment. Other people also refer to it as anomalous diffraction. And if you've ever talked to protein people, you may have heard them talk about doing MAD experiments. I always thought that was pretty cool. That stands for multiple anomalous dispersion. Okay, so this is collecting several different data sets at different wavelengths where this anomalous scattering plays an important role. The elastic scattering is actually given by several contributions, and I know you have seen these F prime and F double prime somewhere yesterday or the day before in some of the lectures already, okay? And it's these F prime and F double prime values that undergo big changes when you get close to an absorption edge of an atom, okay? Now what that allows you to do is you can emphasize the contribution of specific atoms by collecting away from an absorption edge and right at that absorption edge, okay? So if you really want to know what the partial occupancy of that atom is, or what that precise location of that atom is, if it comes to displacements, this is a great way of doing it, and especially when you work with powder and you want to look at mixed site occupancies of certain metal atoms, this is really the way to go if you have access to a synchrotron where you can tune your wavelength, okay, and that way you can actually get this anomalous contribution. What you then usually do is you have several patterns, which means you get that contrast that depends on that one atom, and you actually analyze them simultaneously. This slide shows you how your F prime and F double prime actually change around an absorption edge, okay? As you can see, the F double prime kind of mirrors what the absorption edge of an atom looks like, while the F prime is actually related to a change that is shown here, where you go through a minimum right at the absorption edge, and it's actually given by this equation, okay? So you can indeed make your atoms look very different, and that means that you can look at partial occupancies, look at small static displacements, things like that, and actually get those structural details out. Don't try to do that with something like lab X-ray data on a powder, okay? It's very dangerous, and most of the time you can get something out, but does it have meaning, as Christine already pointed out in her lecture, okay? If you can't get a stable refinement, it's not meaningful. Now, when you work with neutrons, you have to actually worry not just about coherent scattering, but also about incoherent scattering. For X-ray diffraction, we pretty much ignore that anything else exists, so we usually talk about coherent elastic scattering. That's what Bragg's law and everything is based on. Now for neutrons, for single crystal experiments, it's not quite as much of an issue, but for powder diffraction, we actually also have to be aware of incoherent scattering, because that can contribute a lot to the background. Okay? One of the worst culprits here is actually hydrogen. If you look at hydrogen, it has a much larger incoherent cross-section than coherent cross-section. Deuterium, on the other hand, is actually much friendlier when it comes to neutrons. So especially when I was going through grad school, you were pretty much told, don't bring anything that contains hydrogen to a neutron source because it's going to be a disaster. You'll just have background, and you won't be able to do anything with your data. You better work with deuterated materials. As I have been told by people who work here and who definitely should know about this, nowadays, with the better resolution of instruments and the ability to go to the smaller d spacings, where incoherent scattering is no longer quite as bad, apparently, you can actually do experiments where you have some hydrogen in your sample. It's still better to avoid it. So especially if you have a sample that absorbs surface moisture, dry that sample, okay? That's hydrogen that is totally useless because you're not trying to determine where it is. It's just moisture on your sample, okay? And it simply adds to the background. So you don't want that around when you do neutron diffraction. Now, the goal of crystallography is always to get the structure, right? The atomic level structure of our material. Now, I would like to take this slide to contrast single crystal and powder experiments, because that's what we just heard about. And often people learn about single crystal experiments in their regular crystallography class, but how does that compare to a powder experiment, okay? Single crystal experiments. The hardest step most of the time is to grow a good diffraction quality crystal. Once you have a good crystal, collecting data is usually pretty straightforward, both the setup and the access, okay? If you have a good crystal, determining the unit cell is often very easy. Sometimes all you have to do is push a button and the unit cell comes out. Sometimes you have to do more work, okay? But in general terms, it's not really all that hard. You then have to reduce your data and solve, which is determining the approximate structure. Depends on how complex your structure is. For simpler structures, it can still be easy. For more complex structures, you definitely have to pay attention. And then you have to optimize your structure, which is that least squares refinement that Christine introduced. That does require some care, okay? That's when you need to make sure that things are actually meaningful. How about powder? Well, preparing a powder sample is often very easy, right? Anybody ever got a precipitate in the lab? How hard is it to get that? Not hard, right? Collecting data, pretty easy. Take your precipitate, put it on a plate, stick it in a diffractometer. However, if you want to actually get something out of your data, it's also easy to make mistakes, okay? Determining the unit cell. If this is a material that is not known and you don't know what the unit cell might be, this can actually be quite hard. So that's a big difference from single crystal experiments, okay? Solving the structure is even harder and does require expert knowledge, okay? This is not something somebody can learn to do in a simple crystallography class. We often make them solve a single crystal structure because if we have a good crystal, it's fairly straightforward. For powders, not so much. Optimizing the structure is referred to as Rietveld refinement. That is not quite as hard as solving the structure, but it does require considerable care. Okay? It requires more care, I would say, than solving a single crystal structure. So, what is a powder? The definition of a perfect powder is that it consists of an infinite number of small, randomly oriented crystallites. Okay? And that is really the underlying definition that a lot of the programs that you use to analyze your powder data use. Okay? Now, real life, we'll never have a perfect powder because we can't have an infinite number of crystallites, right? But it should be a large number so that we get good averaging. The other question that people often ask me is small. Define small, right? Because nowadays that could mean anything. Some people think that if it isn't a millimeter, it's small. Some people think that if it isn't nano, then it's big, right? So Ideally, you want to have a few microns for your powder, okay? That is small enough that you actually get very good averaging, you don't get intensity spikes, but it's large enough that you don't run into other issues that we'll see later in this presentation. Now, powder samples could be loose powders. That's probably what most of us think about when we hear that expression. It could be films, it could be sheets, blocks, wires. Basically, anything that is crystalline but not a single crystal is a powder sample, okay? It's polycrystalline at that point in time, and we can use powder X-ray diffraction to analyze it. Now, this is just a reminder. Obviously, we've seen what you should observe when you put a single crystal into an X-ray beam. For a single crystal, you have one orientation in real space, and that means you get one orientation of your reciprocal lattice. And if you rotate that crystal, like here, your reciprocal lattice also rotates. Right? So it's pretty straightforward to observe and to analyze. Now, if you have a large number of randomly oriented crystallites, that means all of those orientations exist at once. And so instead of getting one spot for a reflection, you actually basically get a cone of diffraction intensity, because anything at the same distance, d-spacing-wise, will actually give diffraction for that powder. So you get many overlapping reciprocal lattices, and you get diffraction in rings, okay? So if you ever heard somebody talk about powder rings when you stuck something on a single crystal diffractometer, that was probably some ice that formed on the crystal, unless you really didn't have a single crystal there. That is why, okay, you do get diffraction in rings. Now, this is what I have always called somewhere in between, okay? With a powder, you should get rings. With a single crystal, you get one orientation. And this is clearly somewhere in between. As I learned in the last lecture, we should be calling this one a crowder. I really like that expression. So here's a crowder for you. That's what it would look like, okay? Not quite a single crystal, not quite a powder. You do see spots. You kind of see that they arrange in rings, but it's actually not really enough to give you a nice homogeneous powder ring, okay? Now, this is something that we as powder people call a graininess problem. Okay, we don't have enough grains in the beam to get a nice powder ring. We only have certain orientations. Now that can actually cause trouble, okay? Especially on instruments where you actually don't collect data in 2 dimensions like on this slide, but where you collect data in 1 dimension. Okay, if you have a 1-dimensional detector and you scan through this, you'll see this reflection, but you'll completely miss that one, because there's no intensity at this location. Okay, so as you can see, especially if you have something that might be a crowder, 1-dimensional data collection is not a good idea. Okay, if you collect 2D data and you integrate around the rings, you might be able to still go somewhere with the data. Okay, now this is actually data that we collected during a powder high pressure experiment. Okay, and you saw the setup in Christine's talk where you have that little diamond, that little gasket. We are just by the setup limited with respect to how much powder we can put in there. And so unless the powder is extremely well ground and really in that 1 to 2 micron range, you will likely see something like that. Okay, that is usually when my grad students really learn what grinding a powder means. Okay, I usually let them pack 1 cell just for the fun of it when they say they've ground it enough, and most of the time they haven't. So if your advisor tells you grind something well, do it. Surprise them. Now, this was a data set that actually had a better ground powder. Okay, again, these were some high pressure data collected on a 2D detector. Now, in case you're wondering why these rings don't really look like rings, it's because I used a camera and I took a picture of the computer screen at an angle. Okay, so it's a simple issue of photographic physics, not diffraction physics in this case. They were actually perfect round powder rings, but if you took the picture straight on, you got the reflection of the flash and you couldn't see anything. So needless to say, I took the picture like that. Now, most of the time, we don't display powder data like that, okay? Very rarely will you find 2D patterns when people show you powder data. Most of the time, we display the data like this, 1-dimensional, And you can have any kind of function of Q down here. It could be Q, it could be sine theta over lambda, it could be D, it could be theta, 2 theta, whatever people prefer to plot their data in. But usually it's one-dimensional data. The way we get these data is we actually basically masked our beam stop, okay? And if we know the sample to detector distance, we can actually integrate all of our data, okay, and just display it as one-dimensional data. So we eliminate any of those effects of some slight irregularities around those powder rings. But because we have such a limited amount of powder in a diamond cell, most of the high-pressure experiments will be done with a 2D detector. Now, why would you use powder diffraction? In the old days, powder diffraction was mainly used for phase identification and not really for anything much more sophisticated. Nowadays, that has changed quite a bit because we have better programs, better computers, better setups. One advantage that powder diffraction has over single crystal is you can use it on any sample. If you can mount it on a diffractometer, you can measure it, okay? That's nice. So if you have a material for which single crystal growth is difficult or maybe even impossible, maybe you're working with a metastable material, powder methods may be your only option, okay? Now the other reason, I kind of borrowed that expression from Jim Kovacs, who is a very big fan of powder diffraction, is he always says real-life samples usually don't come as single crystals, right? How many things that we use in daily life are single crystals? Hardly any of them, right? So most engineering materials, formulations, and so on, by default, are not single crystals. So if you want to analyze them, powder diffraction is the method of choice because you can use it on mixtures, okay? Another really cool thing about powder diffraction is that you can analyze the peak shapes, and that can actually tell you something about particle sizes, stress, defects, all of these things that engineers really pay a lot of attention to because that is what determines the performance of the materials. So powder crystallography before Rietveld was, for the most part, avoided when it came to structure determination. And that was due to the fact that there was no simple way of dealing with the data, okay, especially in the old days when you had films. But even after you had better detectors, it was still not easy to deal with because you had to first of all integrate your intensities, and until computers became more powerful, that was done manually, okay, where people cut out their peaks and weighed them to figure out how intense that peak was, okay? It may sound really weird, but that is actually what people used to do in the old days, okay? The other problem you had is, because we usually have our data displayed in one dimension, you get a lot of overlapping reflections, right? If you have close d-spacings for two reflections, you're not going to resolve them. You might even have exact overlap in some higher symmetry systems. So what do you do with them? Well, one option was you discarded them. That can result in a lot of reflections being discarded, depending on your material. The only alternative was to rewrite the existing single crystal software so that you could refine things by using the sum of the overlapped reflections. Now, if that sounds like a pretty bad idea to anybody else, you're on the right track of why people said avoid powder diffraction when it comes to solving structures. And to some extent, that's still true today. If you can grow a single crystal, grow it for structure solution, okay? There is nothing that beats that. But if you're stuck with dealing with powder, you have a lot more options nowadays compared to what was possible back then, okay? What was much more common in the old days was the simulation of a powder pattern, because it was pretty easy, right? It follows the same laws of diffraction as single crystal diffraction. And what you basically then did was you drew conclusions based on whether patterns looked similar. Especially when you had isostructural compounds, that worked very well. So it was mainly based on visual comparison. Once again, mainly people used it to identify what phase or phases were present in their powder sample. Now, nowadays, what can we actually do with powder data? And we are not going into too much detail on any of these, but this is supposed to give you a flavor of what you can actually use this method for. Phase identification is still the most common use of powder diffraction, okay? It's a qualitative analysis tool. You search your pattern against a database, and you can identify phases that are present. Starting materials, known target compounds, likely impurities, or if there is an isostructural material in the database, you can still identify it by pulling up something that has the same type of unit cell. Okay? Phase fraction analysis, which is what we call quantitative phase analysis. You can apply this to a mixture of 2 or more crystalline phases. This, by default, is something you can't do with single crystal diffraction, okay, because a single crystal can't be a mixture of more than one phase. What you do is you compare the intensities of selected peaks of all the phases. In theory, this can be done with 2 peaks, one from each phase. Okay? If you want to get the best data, you use more than 1 peak. I think that goes without saying. Okay? Unfortunately, it's actually still kind of an industry standard in some branches of industry that they have their high throughput stuff and they write their program to look at the intensities of 2 peaks. Okay? There are much better ways of doing that if you really want to get a good answer. Now, if you want to get accurate values out, you should use some kind of a standardization. Okay? Oops, I didn't mean to go on yet. You could, for example, prepare something where you have 2 phases that you're trying to analyze in known quantities. So you need to determine what the average height of those peaks actually should be. Okay? Because it's not like NMR, where a peak integrates to 1 hydrogen or to 3 hydrogens. Okay? Your intensities are related to its structure factor. So you can't just say, if my 2 peaks are equal height, I have equal amounts of these 2 phases. You need to know what it actually relates to. Okay? One thing to be careful about is there is the possibility of amorphous components. They contribute weight, but they don't contribute intensity to your diffraction pattern. What else can you get? You could actually use powder diffraction to get good lattice parameters of your sample, especially if you do an experiment where you change certain conditions. One mode of analysis would be to get accurate lattice parameters of a compound of known structure. The second one would be to actually determine the unit cell by indexing your sample. In both cases, you need good, reliable peak positions. Okay? If there are errors in your peak positions, they will mess up your results. You can also do Rietveld refinement, which is structural analysis. This is a least squares based minimization to get the best fit between a structural model and a powder pattern. You do need a starting model, otherwise you cannot do this. Okay? But you can apply this to very simple structures, to very complex structures. There are people who have actually refined powder data for proteins. Okay? You could do it on one phase, on multiple phases. One really nice thing is that you automatically get the phase fractions out of this method. Okay? And you also get the lattice parameters, and you're using all of the peaks in this case. So this is actually kind of the gold standard for if you really want to get good phase fractions or good lattice parameters, do Rietveld. Again, you need good data if you want to get meaningful results. What else can you do with powder? You could try to determine a structure from powder data. As I said, that's not trivial, but it's possible. Okay? It is subject to the same laws of physics. The only issue we face is data overlap. Okay? Usually, this does require synchrotron or neutron data. Okay? Structure determination from lab data, in very rare cases, may be possible and actually work, but in general, you need better data than that if you want to determine a structure from powder. In addition to the good data, you need very good crystallographic knowledge because a lot of things can go wrong when you try to determine structures from powder. Are we done yet? Not quite. You can also look at phase transition behavior with powders. This refers to in situ diffraction experiments. And in this case, you're changing a parameter of the surroundings. That could be temperature, could be pressure. You could actually do kinetic studies. That's, again, something that often uses 2D detectors, okay, where you go to a certain temperature and you just keep taking snapshots of your sample to watch how fast a certain phase converts, for example. You could also do studies where you're looking in a certain atmosphere. Okay? I know that Powgen, for example, has a gas handling chamber where you can work with partial oxygen pressure, something like that, and you watch how your sample responds to that. All of these obviously require specialized setups where you can change one of those parameters, okay? But it is available, and it can give you some really cool insights into your materials. We are still not done. You can do even more with powders. One interesting thing that especially engineers look at a lot is line shape analysis, okay? For single crystal experiments, we usually check to make sure that the peak is a good peak, right? Because we want to make sure it's a good single crystal. But other than that, we put a box around it and we integrate the intensity. That's all we really do when we work with single crystal data. For powder data, in some cases, you may be more interested in the line shape than in anything else, because the width and shape of the Bragg peaks actually tells you a lot about your sample. The width of the peaks is actually inversely related to your crystallites. So really small crystallites give you really broad peaks. And that is why I said the ideal sample for structural analysis is about 1 to 5 microns. Okay, if you go to nano size, you get broader peaks, and that means you get more overlap. So for structural analysis, that's not the most desirable thing. But if you're working on nanomaterials, obviously you want the broad peaks, okay? That's the best thing you can see. So you can actually estimate the crystallite size of nanoparticles using your powder diffraction data. You do need to use a standard though, because your instrument will contribute a certain amount to your peak width as well, okay? And so you need to correct for that, because otherwise you're not going to get an accurate crystallite size. Turns out that microstrain in your sample will also broaden your peaks, okay? And that can be very important, again, from a performance point of view for materials. There could be multiple things that contribute to that. It could be atomic disorder, dislocations, vacancies in the material. You could have residual stress just from the processing of the material, okay? It turns out that the angular dependence of the peak broadening is different for the crystallite size and the microstrain. So if you do really careful experiments, you can actually extract information about both from your powder data. Other defects will also affect your line shape, okay? Stacking faults, anti-phase boundaries, things like that. They are often more difficult to treat though when it comes to analysis of your data. The last thing that you can do is so-called texture analysis. Okay? We talked about an ideal powder being an infinite number of small, randomly oriented crystallites. Texture is the opposite of random orientation. Okay? It's something where you have special orientations. This could be desired. Okay? If you ever met people who work with thin films, they often want to grow epitaxial films with a perfect orientation. You can analyze whether you have that perfect orientation by running a powder diffraction pattern, okay? Whenever it is not something that you're actually trying to make, it's usually not referred to as epitaxial growth, but rather as preferred orientation. And in many cases, that's actually not something we desire in powder diffraction. I will be honest about that. So what kind of information can you get from your powder diffractogram? Turns out any diffractogram contains 3 kinds of information. You got peak positions. They are given by Bragg's law, right? Peak intensities, they are related to the structure factors. And you also have peak shapes. And that's something we don't worry about in single crystal experiments, apart from saying, is my peak shape good? For powder experiments, we actually may analyze all 3 of these, okay? So let's start with the peak positions. What kind of information do we get from the peak positions? Obviously, our unit cell dimensions are related to our peak positions, right? D-spacing can be correlated to our unit cell constants. Now, this could mean that we are doing a refinement if we already know the unit cell, or we may be determining our unit cell from scratch by indexing. The second piece of information that is inherent to the peak positions, and Christine very nicely pointed that one out, is that we can look at the possible space groups. People often forget that that is also something that has to do with the peak positions, okay? Because we are looking at systematic absences there. If peaks are missing, that means we can start narrowing down our possible space groups. Obviously, peak positions are also used in qualitative analysis, because if you ask what is in my sample, you need to know where the peaks are showing up. It turns out that this last one is the one type of analysis where approximate peak positions are often sufficient for getting your answer. Okay? Everything else actually requires good data with accurate peak positions. So, how do we actually know whether our peak positions are correct? That's a good question, right? We often take that for granted. And if you work at a national lab, usually your beamline scientists have taken care of that for you, and you really don't have to worry. Okay? But if you work on a diffractometer somewhere at a university, sometimes it's a fine assumption, and sometimes it's a very bad assumption. So how do you check? Well, you could use a standard to check the alignment of a diffractometer. And many of them are commercially available: quartz, silicon, ceria, alumina. NIST provides quite a few of them. The diffractometer vendor may have given you one with the instrument. The easiest to use ones come as pressed solids. So you have no sample prep. You just stick it in the diffractometer. You measure your data, which for lab diffractometers means your sample height is predefined. That's something you have to watch out for when you prepare your lab powder samples. And then you figure out what your peak positions are, and you compare it to where they are supposed to be. If they are identical, congratulations, you don't have any errors. If they aren't, you can actually construct a calibration curve and correct your data accordingly. Okay? Now, that's a lot of work, isn't it? Who likes to do that? Come up with the mathematical equations to correct your data, apply it to every single peak. We don't like doing that, do we? Another big opportunity in powder diffraction is to use an internal standard. Okay? Because again, a powder can be more than one phase. So why not mix a standard in it? That's what we call an internal standard. You can pretty much use any material that is available as a powder that has well-established lattice constants. Of course, using a certified standard has the advantage that you're really sure about the lattice constant. Okay? Now, if you're planning to do Rietveld refinement of your data, you can simply refine another phase for your standard, okay? And you can constrain any types of errors to be identical for your standard and your sample. If you're on a lab diffractometer and you might have a height error, it should be the same, right? It's for the sample, not for a phase. If there's a 0-point error on any diffractometer, it will be the same for any of your phases in your sample. So your standard, because you know what the lattice constants are, allows you to refine errors in your data and then apply them to all of the phases that are present in your sample. Okay, does that make sense? If you really have a choice, choose a standard that has similar absorption properties to your sample, because that way any absorption-related errors will be identical for your sample and your standard. Okay? You don't always have that choice, but if you do have a choice, that is really how you should do it. So, that's how we deal with peak positions. How about peak intensities? Obviously, the big thing contained in peak intensity is information about the structure, right? The positions and types of atoms, the site occupancies of atoms, and the atomic displacement parameters, which we so often call temperature factors, but they could be from static disorder as well, right? You need accurate intensities if you want to do quantitative phase analysis, right? Otherwise that won't work. You also need that for Rietveld. And most importantly, if you want to attempt structure solution from powder data, you better have good intensities, okay? Because that is basically where your structure comes from, right? From the intensities. Whenever you analyze anything related to peak intensities, you should be using integrated peak intensities, because that eliminates broadening effects, okay? If you just go by the height of a peak, if the peak is broader, the height will be lower, but you will still have a lot of intensity under the peak. One thing to keep in mind is that your experimental setup will also influence your intensities, okay? That's why we usually say intensity is proportional to the square of the structure factor amplitude. It is not identical, okay? There are some other factors that go in between there. And the sample itself will actually affect your peak intensities as well, especially if you run in transmission and you have some absorption. Now, one of the things that you may be less familiar with, unless you have done a lot of powder work, is this preferred orientation that I threw up there on that slide, right? What that refers to is that some samples simply do not show random orientations, not random intensities, so we call it preferred orientation. It means some orientations are more prevalent and others are underrepresented. And in really severe cases, you may completely be missing quite a few of the lines and only observe certain lines. Okay? Now, in epitaxial film, if that's your goal, you're going to celebrate if you see that. Generally, for powder data analysis by Rietveld or even structure solution, this is not a good thing. Okay? And here's an extreme example of preferred preferred orientation. Okay? Here is a pattern for alumina that is done with random orientation, okay? And so you see all of these different lines. I then decided to mess with it and just simulate a pattern where I put in a preferred orientation coefficient. And look what I get for the same structure. Okay, now this is a very extreme case. Most of the time, your data from your real-life powder sample will not look quite as extreme. Okay, but this is what you would see for an epitaxial film. A lot of the lines are simply missing. Okay, now if you know your structure and you're sure about what your phase is, you may still be able to refine this data set. But if you wanted to solve a structure from powder data, this would be the end of it. Okay, because you're missing most of your peaks, you're missing most of your integrated intensities, and all of these integrated intensities are basically wrong compared to what you would predict with the structure factor equation. Okay? So preferred orientation for structural determination from powder data is usually a killer. How do you know whether you have preferred orientation? Good question, right? Now in this case it's extreme, easy to detect. One way to figure it out is to take one sample that you pack loosely and one sample that you really pack down, and you run the two patterns, and if the intensities look pretty comparable, your sample probably doesn't give you any preferred orientation issues. If the intensities don't look the same, there's a good chance that your sample has a tendency to orient. Okay? Make sense? The only real way around that is to collect data in a capillary. Okay? Because the capillary spinning actually eliminates a lot of those issues. At a synchrotron, easy to do. At a neutron source, you usually have a can anyway. Okay? On a lab instrument, many materials will give you too much absorption to actually carry out that experiment. So if you have a sample like that, most of the time you will require national facilities to get good data. Okay? Another issue that you might run into with your powder sample is something called a surface roughness effect. Okay? Now this applies only to flat plate samples, but how many people here have actually done powder diffraction? Quite a few of you. And what's your standard setup? Probably a flat plate sample, right, that you mount on your diffractometer. That's the most typical way of doing it. There could be something going on that is called surface roughness. And I put a little sketch here to illustrate what that really refers to, because surface roughness is actually a microabsorption problem. Okay? If you're in the mountains and the sun is really high up, there's no shadows, right? If the sun starts going down, you start seeing shadows. The sun doesn't reach everywhere. The same thing happens with X-rays if you have a rough or mountainous surface. Okay? And it turns out that the X-rays that hit on this side have to travel through material to get to the detector. And so they will get absorbed, and the lower your angle is, the more absorption you have. Okay? That's obviously an issue because it reduces your intensity, and your program assumes that you don't have any such intensity reduction. And this graph actually shows you how severe that issue can be. Okay? If you have something that is about a 40, 45 micron powder, at 15 degree 2 theta, you only see about 1/3 of your intensity that you should see. Okay? It's a very severe effect if you have a rough surface. So that's something to watch out for if you are running powders with a flat plate setup. And most samples do have peaks below 30 degrees. The last one that we had to address are peak shapes, right? They contain information about crystallite size, especially if you're below 100 nanometers. Microstrain, because that can lead to a range of lattice parameters. Ordered defects, but there's also a contribution from the instrument that we cannot neglect. Okay, that's the finite source size. We have some divergence, your slits, your detector, everything contributes. It turns out that a lot of these effects can be isotropic or anisotropic, so they could apply to all reflections or only to some of them. Quantitative analysis is best done by using a standard that has no crystallite size or strain broadening, because that way you can determine what the instrument contributes. So what do we mean with all of this? Here's an example of some of the peak shapes, and I think that's the one slide that somehow is missing in what I uploaded. I will have to resubmit this. I realized it got lost. Common peak shapes are either Gaussian or Lorentzian. Okay, so often neutron reactor data and X-ray lab data are described with Gaussian or Lorentzian peak shapes. Many programs use a so-called pseudo-void. Okay, a true void would be a convolution of a Gaussian and a Lorentzian. A lot of programs were written when computers weren't that good and fast yet. So a pseudo-void basically just sums up the contributions of the Gaussian and Lorentzian. It's computationally less demanding, and in many cases it actually describes your peak shape fairly well. But this is something to keep in mind, that you need to select a peak shape that actually matches the instrument on which you collected the data. Here is a little graph illustrating the sample-related peak broadening. The crystallite size basically comes from the fact that you should have a delta function. If you have an infinite crystal, your crystal is finite, you get broadening. Okay? And it's actually described by the Scherer equation. And for a lab instrument, your full width in half max is 0.9 times lambda divided by the crystallite size times cosine theta. Okay? This is actually only one contribution. Your instrument also makes a contribution. So your measured full width of half max has to be corrected for that. Strain broadening is nicely illustrated here. Okay? If you have uniform strain, you just shift your peaks because your lattice constant changes. If you have non-uniform strain, you get a distribution of lattice constants, and therefore you get broader peaks. Okay? Now, I did mention that these effects can be HKL dependent, and I actually do have one very nice example that one of my grad students collected, where she got this X-ray diffraction pattern, and there is one aluminum sample holder peak, but other than that, everything is matched by a single view card. Okay, now if you didn't have that view card on there, you would probably not guess that this is one phase, because some peaks are really broad, some are really sharp. Turns out that this sample grows little platelets. It's hexagonal, and the short direction of these platelets is along the c-axis. So anything that has an L contribution here gives you broad peaks. Anything that doesn't have an L contribution gives you sharper peaks. Okay, so you could see that in your data. Beware. Quick note on detector options. We can collect data 1D or 2D. Okay? Area detectors give fast data collection. Especially on high-intensity synchrotron beamlines, you may be able to collect your data set in less than a second. That's nice, especially for kinetic studies. The trade-off is the resolution. Okay? Point detectors allow for very high-resolution data. Okay? Ideally, you actually have a single crystal analyzer mounted between your sample and the detector. That's the setup that 11BM uses to give you really high-resolution data. They actually use a set of 12 detectors to improve collection speed. But in that case, it takes you about an hour to get really good quality data. What do these things look like? Here's an example of a 2D detection. Okay? Basically, you have a setup. This is the diamond anvil cell that we used. And then you have an image plate mounted right over here on which you collect your pattern. This is a setup at 11BM, where you have these 12 detectors with single crystal analyzers in front of them, and that's how you collect your data. Now, I believe you've already heard a little bit about neutron sources. Is that correct? So you have some idea that we have two options for collecting neutron data: reactor sources and spallation sources. How your powder experiment is set up depends on which type of source you're using. In a reactor, you constantly create neutrons by a nuclear chain reaction. That means there's no time structure to your neutrons, and so your setup is actually pretty similar to what you would see on a lab diffractometer. You need a monochromator to figure out what neutrons you use. The main difference is you don't really have a line source like you would have in a powder X-ray in the lab. You actually have a broader distribution of neutron wavelengths, but you basically just take a cut with a monochromator, and that's what you collect your data with. You do need large samples because your intensity is not always that high, and you just don't have the same scattering cross-section. The good thing is you don't have any form factor fall-off, so you get good quality data at small d spacings. But depending on the wavelength that you choose, your minimum d spacing may be limited by the fact that it can only go to a certain 2 theta. The spallation source, as you probably have learned, you basically have pulses of protons, and you then create some neutrons out of that. Okay. And these neutrons come in pulses because you're using pulses of protons. And I do have this little schematic that I like to show in my X-ray class of the SNS, given that we have a very powerful spallation source right here in the US. Those neutrons are then fed into your guide hall and then to your instrument. The big advantage is you have a time structure here, because your neutrons are particles with a mass. They have a wavelength associated with them, and so you have detector banks at fixed angles, and each detector can actually collect the entire diffraction pattern by detecting when the neutrons arrive there. Okay? Your d-spacing range will depend on the angle of the bank and the spacing between the pulses. Okay? So there's often more than one bank, especially on older instruments. Here's an example of one of the more old-school time-of-flight neutron instruments. This was the special environment powder diffractometer that used to run at IPNS up at Argonne National Lab. It's actually the first neutron diffractometer that I ever got data from. And as you can see, there are certain detector banks, but there's also a lot of empty space. Modern instruments try to make use of all the neutrons that are generated. So here's an example of PowGen, the schematic, and a real-life picture, where you can see that basically the instrument is supposed to be completely surrounded by detectors, and everything is focused together. So it's a somewhat different setup, but it gives you very good data. Now, beyond search match, the big step forward was the Rietveld method. Okay? It was in the late 1960s that Hugo Rietveld introduced a whole pattern fitting approach, and that really put powder diffraction into a different time. Okay? Instead of simple search match, you could all of a sudden do things. He did this originally with neutron data. In 1977, R. Young actually applied it to X-ray data, and the increase in computing power is what has made it a routine tool nowadays. You can use it to verify structures, get accurate lattice parameters, look at microstructural sample characteristics, phase fractions, and all kinds of things. One thing I would like to mention at this point is Hugo Rietveld actually passed away 2 weeks ago. Okay, some of you may already know that. So it's the 50th birthday of the Rietveld method, the 100th birthday of powder diffraction. It's kind of sad that he couldn't quite make all the celebrations that are planned this year. Now, what was the big thing that he discovered? First of all, he witnessed that computers can really help with crystallography. But he then also realized that computers can handle individual data point intensities, and that they can even calculate something when you have overlapped reflections, and that they can optimize things where they allow the intensities of different reflections that contribute to a data point to vary. And that sounds really simple nowadays, okay? But that was a huge breakthrough compared to refining sums of reflections. Just like single crystal methods, this one is a least squares based minimization in which you try to get the best fit between a structural model and your pattern. It is demanding as it is nonlinear. And you as the user have to decide what variables you touch. Note that every data point in the pattern is an observation. No intensity also tells you something about your material. Okay? You're fitting the full pattern. That's very different from single crystal data. Your background, your peak shape, sample and instrument contributions, all of that needs to be taken care of. And you do need good data and a starting model to do this. Okay? What are some of the parameters? Here's a list. And I certainly encourage you to go back to it if you ever deal with data. Okay? Structural variables are the only ones that we would vary in a single crystal structure solution experiment. What are the atoms, fractional occupancies, displacement parameters? We need to take care of background, peak shape, unit cell constants, wavelength, if we don't know it exactly, 0 points, sample height, transparency. We could have to correct our data for absorption, extinction, roughness, preferred orientation. So there's a lot more to do than in a single crystal experiment. What can you do with it? It works on pretty much any structure if you can come up with a structural model. You can refine several phases, mix occupancies, several data sets together. There really aren't many limitations. Okay? You can refine engineering properties. The limitations are that you can't determine absolute structure, for starters. HKL, H bar K by L bar overlap completely. Parameters can be correlated, and it's up to you to decide whether or not you can truly vary all the parameters. If your data are too limited, you will not get physically meaningful results. Okay? You may have to use constraints or restraints, and it only works if you have a good starting model. Okay? Once again, you will be the judge of your Rietveld refinement. So working with powder data is actually quite difficult because you are the one who has to judge whether things make sense. On the last slide, I put together some resources for you. Okay? If you want to find more things, the Rietveld mailing list is definitely a great place to get advice from people who have done this a lot more than you have. Okay? A couple of books. There are more good books out there. And there's definitely websites where you can get the software. So hopefully quite a few of you will have some fun with powder diffraction and actually get some good results out of it. And with that, I will be happy to answer any questions. So how much do I account for the shape of the peak, not just the basic width that comes from the instrument when I look at the broadening? So what we usually do is we run a standard over a large angular range. And then we extract the full width at half max. So the asymmetry will affect that a little bit. But you know, if we went further down to the peak tails, the asymmetry would have a way bigger contribution to our peaks. So the full width at half max, you know, some of that is just basically taken into that. What we then basically do is we plot the full width at half max we see for the standard as a function of angle. And in most cases, that is actually a very simple function that we find. Often over the range that we extract peaks where we can extract single peaks, we basically see something that stays close to constant. Although if we have materials where we go to 60, 70 degree, we may have to apply a function that actually shows an increase. But we then basically just subtract that out, okay? And the whole thing is that the asymmetry is usually due to instrument contributions, to the axial divergence. So that one, once again, should be the same for the standard and for the sample where we are trying to analyze, for example, crystallite size.
I have a question. Are you
So is there a program that handles preferred orientation refinements better than others? If you know what your preferred orientation direction is, most Rietveld codes actually have the March Delays model in there where you can enter that. That's how I created that really extreme plot, okay? If you aren't sure what your exact preferred orientation is, that's when life gets a little more tricky. And the best approach to that is really to use something called spherical harmonics, which basically allows the program to vary it. That is implemented, I know for sure, in GSAS as well as GSAS2. It does not work in a few of the cubic space groups. I don't know what exactly in the coding causes trouble, but it doesn't. Topaz also does it. I believe by now it actually also has been implemented in full prof. When I first learned full prof, it really didn't do so well. So back then, if I had to deal with preferred orientation, GSAS was my main choice. So that does work. It can be tricky. Turn other things off because other things might run away otherwise. So, or collect capillary data, which may eliminate a lot of those effects.
I've seen some papers where they determine the crystallite size via the Scherer formula and then use alternative characterization methods to determine the crystallite size and found that it did not match up well. Are there any, I guess, considerations that we need to take into account?
So basically, there are people who publish a crystallite size from Scherer and people, and at the same time also look at it with SEM or TEM usually, right? And they don't get the same numbers. The most common reason for that is people are not taking into account the instrumental broadening, okay? I've reviewed more than one paper where they never took that into account. And I always send them back and say, you need to run a standard, you need to correct it, and usually the numbers match better then. The second thing is, remember that what X-ray looks at is the crystallite size. What SEM gives you is the particle size. They are not always identical. So if SEM gives you something that is bigger, it may well be that you have multiple little crystallites in that particle that you see. So that is the second very common reason for that.
So is there any way to determine whether or not you have amorphous components and how much of that component you have?
So can you determine if there's amorphous and quantify it? Yes, it's not easy, okay? I've actually done it myself. What you basically do is you take a fully crystalline standard, and so I mixed 50-50 weight percent, and I refined my phases. I didn't get 50-50 back. I know the remaining weight has to be an amorphous component. What you really would want to do to get a good answer is do a 2-to-1, 1-to-1, 1-to-2 mixture and see whether you get about the same number out, okay? But yes, so you can estimate it that way.
Do you have a suggested way of getting a standard onto a sample that is a thin film on like a wafer?
How to get a standard onto a thin film on a wafer?
I get a lot of problems from like sample shadowing on the detector that never make it match the background of the standards that I take. Which always makes it terrible to calculate what my backgrounds are. So I like your suggestion to put it direct on the sample, but I'm looking for...
Yeah, that could be difficult because you'll definitely have a slight height offset if you sprinkle it on there, you know. That might be the closest thing you can get to an internal standard at that point in time. I assume if you talk about shadowing on the detector, you're talking about a film that does have some variation, some surface roughness basically, you know, so that will already lead to some effects. The best thing you can probably attempt is put a really, really thin dusting on, you know, and see what that does. That will at least give you a starting point. But yeah, that's hard because then you can't really do an internal standard very easily.
Thank you.
Another thing our lab does is if there's a wafer that you know the reflections of and you can observe those reflections in your pattern and you know the thickness of your film, for example, by XRR, you can figure out how the peak of the wafer
Yes, you could use the wafer below it if you see reflections from the wafer and you know the thin film thickness. That's correct. Then your error is basically the thin film thickness there, you know, how precisely you can get that one, especially if it varies. But yeah, that one is a little more difficult. The best thing you can do is make sure your instrument is well aligned with an external standard, okay? And just bug the people who are responsible for it until it is well aligned if necessary, because then you know that you don't have to worry about a 0 point, and you know that any errors would come from, you know, some height offset of how the film is mounted, things like that. So, do we have time for one more, Brian?
One more, and then we'll go to Mary.
What kind of standards or what kind of material would you use for standards that you don't have a peak broadening, like a peak broadening effectively to the size of the crystallite?
So lanthanum hexaboride is often used as a peak shape standard. That one is certified by NIST, and they actually tell you what kind of contribution you should get. We've actually found that the silicon that we have from NIST really doesn't have much contribution to the peak broadening either, at least not for the resolution of our instrument. If you go to something like a synchrotron, you know, you may have to worry more about that. But for a standard lab instrument, that works pretty well. Don't buy the really cheap silicon somewhere else, because that can give you quite different peak shapes. One of my students went off to work for a company that decided to save money, and yeah, that didn't go well. So, and sometimes just annealing your material can help, you know, make sure that you don't have any of the strain left. So that is what they eventually ended up doing to make the silicon acceptable.